Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue looking at earthquakes and the Earth's interior. So in this video we're going to be focusing on what the seismic waves indicate about the Earth's interior, and this is going to correspond to section 12.15 of your textbook. Now, we know that when an earthquake occurs, it's going to produce seismic waves, which will radiate out from the hypercenter of the earthquake in all directions. So we can see in this instance, here's our hypercenter for our earthquake, where the movement's actually occurring, and we can see that the seismic waves are going to push out in all directions from that location. So what's actually going to happen to the waves as they move through the Earth's crust? Now, we can see here's our hypercenter once again, and this black line here is representing the seismic wave. So in this case, we have a seismic wave that's pushing down, and it's moving towards a boundary between two different layers of rock. Now, at this point, two things can happen. One, the wave can be reflected back towards the surface, or two, the wave can be refracted as it crosses the boundary. Now, refraction essentially means that the angle at which the wave is traveling shifts. Sometimes it can become steeper, like this one, and sometimes it can become shallower, like this one. And we're going to cover a couple of examples of how refraction changes the path of a wave in the diagrams below. So in this situation, we have a transition where we're moving from a faster material here to a slower material here. When we're talking about faster and slower, we simply are referring to the efficiency with which the wave can move through the material. The more efficiently it can move through the material, the faster it will be capable of traveling. So a very, very dense rock where the minerals and the atoms that make up the minerals are very tightly packed together will often be faster because as the atoms are more closely spaced, it means as they move towards each other, they'll push each other earlier, and it means the next, that'll then apply the force to the next atom in the chain. In contrast, slower materials will often be not quite as dense, and this lower density will mean that the wave will tend to move through them more slowly. Now, in this instance, as I said, we're moving from faster to slower. So once again, here's our hypercenter. So here's our earthquake, and this is our seismic wave coming from our earthquake, and our boundary is marked right here. So in this case, as you can see, the transition from faster to slower causes the wave to essentially become steeper. So it's refracted and it's changed the path of it, and the angle of the path has steepened as it's transitioned from slower to faster. Now, this is the kind of situation we may get if we're transitioning from a solid to a liquid. So imagine that you're transitioning from the lithosphere into the asthenosphere. So this would be your lithosphere up here, and this would be your asthenosphere down here. So as your wave emanated from your earthquake, it moves down through the lithosphere, it hits the lithosphere-asthenosphere boundary, and we would see the angle of the wave change as it was refracted as it crossed the boundary. Now, when we have the reverse situation and we're moving from a slower material to a faster material, you will see that the angle of the wave shallows. So once again, here's our hypercenter where our earthquake seismic waves are being produced. Here are our seismic waves moving down. They're trying to cross the boundary, and as they cross the boundary, the wave is being refracted, but because we're moving from slower to faster, we can see that the angle of the wave has shallowed. And we will also see the same thing if the seismic wave is going upwards. In these two models, it's been going downwards, but in this case, as we can see, it's rising up. So in this case, we're transitioning from fast to slow. So it's the same as this model here. So here's our seismic wave coming along, and it's moving towards our boundary. And as it transitions from a faster material to a slower material, we can see that the angle at which the seismic wave is moving has increased. It's become steeper. So refraction will change the path that our seismic waves take as they move through the Earth's interior. And this is going to be extremely helpful when it comes to trying to work out what, the size of the Earth's internal layering, and also what the Earth's internal layering is made of with respect to its physical properties. Is it a liquid? Is it a solid? So if we look at this diagram, what we're doing is we're showing a very simplified diagram of the path which can be taken by a seismic wave. So here is our hypercenter, so our earthquake is occurring here, and these lines just simply represent the seismic waves emanating from the hypercenter. So this black line represents the path which is being taken by a seismic wave. So as you can see, as we're coming along, what's happening, or we're coming down here, and we can see that as we're crossing across this boundary, our wave is refracting. Okay, and we can see that if it had gone straight ahead, it would have continued like so. So we can see the angle at which this wave is traveling has shallowed slightly. And this would suggest, if we go back to the previous slide, that what we're looking at is a transition from a slower material to a faster material. So this would be the slower material, and this would be the faster material here. Now, once it's passing through this layer of faster material, it's hitting this next boundary, and you can see that instead of moving down into the layer below, the seismic wave is actually moving along the boundary itself. Now, once it decides to move off the boundary, you can see it's moving back through the fast layer here, and then as it hits this boundary again, we can see in this case the angle at which the wave is moving has steepened, so that is telling us we're moving from a faster material here to a slower material here. So you can see that the path being taken by this seismic wave is telling us something about the material which it's moving through. Now, if let's say for instance, if both of these materials had the same physical properties, as the wave passed across the layer, you would simply see it take the same path. It would then move along, and then it would come up and continue on the same path. So if there was no change in the physical properties, you might expect your seismic wave to reappear somewhere about here. But because the wave refracts as it crosses from these materials with different physical properties, you can see the location at which the wave re-emerges is actually different. So the subsurface is affecting the path which the wave is taking. So how can we use the path that seismic waves take to tell us about the Earth's interior? So in this model, you can see that we have a situation where we have the same earthquake occurring, but we're looking at two different monitoring stations. The monitoring stations are marked out here as these grey cubes. So you'll notice in this first scenario, we have our earthquake occurring right here, relatively near the crust mantle boundary. Now in this particular model, the mantle rocks are going to represent the fast material, and the crust is going to represent the slow material. Now, in the situation where the monitoring station is relatively close to our earthquake, what's going to happen? Well, the thing that's going to happen is the waves that move through the crust are going to arrive first because they are traveling over a short distance. In contrast, the waves which move down and cross the boundary between the crust and the mantle are obviously taking a longer path. So our waves are coming down from our hypercenter, they're transitioning from the crust into the mantle, so that's moving from a slow material to a fast material, and this means the angle at which our seismic waves are traveling is going to shallow. So our seismic waves change their angle, they curve as they move through the mantle, and here they are transitioning from the faster mantle into the slower crust. So that's going to cause the angle of the seismic waves to steepen. But obviously, as you can see, the distance that the seismic wave is covering is greater than the distance that this seismic wave is covering. So by the time that this seismic wave here, which has just passed through the crust, is beginning to arrive at the seismic station, this wave, which has moved its way through the mantle, as you can see, has taken, has covered the same distance, but it's nowhere near arriving at the monitoring station. So typically, in the situation where you have a monitoring station relatively close to the earthquake, these waves that just move through the crust will arrive first. Now, in this opposite scenario, we have the same earthquake occurring, but we're looking at a different monitoring station. Now, in this case, we have once again, we have some seismic waves that are just moving through the crust. And in this case, we have the seismic waves moving through the mantle. So once again, our seismic waves are moving down. They're transitioning from the crust to the mantle. So they're moving from a slow to fast material. This means the angle's shallow. So we're getting refraction. So the path that the seismic waves take is changing. So it shallow slightly. As we can see, the wave then moves through the mantle, and then it's moving back from the mantle into the crust, so it's moving from fast to slow. So the refraction is going to cause the angle of the seismic wave to become steeper, and then it's going to be detected at our seismic monitoring station. Now, in contrast, the seismic wave that's moving through the crust doesn't arrive at the same time, it arrives afterwards. So you can see we have the reverse situation. So the question is well, why is this happening? Well, in this model, because we have this greater distance which the seismic waves are travelling, the physical properties of the layer are going to have a greater effect. So in the first model, the seismic waves that moved through the crust here are going to arrive first simply because the distance is shorter. In this case, we can see the seismic waves moving through the crust are going to progress quite nicely, but the seismic waves that move down into the mantle are going to be travelling through a denser, faster material. And so that means that the seismic waves that make their way down into the mantle rocks are going to start moving faster relative to the seismic waves that are moving through just the crust. And so what's happening is the seismic waves that are taking this path, even though it's longer, begin to accelerate and they move faster, and so they overtake the seismic waves that are just moving through the crust, and so we can essentially detect these seismic waves first at the more distant monitoring station. So you're thinking, okay, well, how is that actually going to be helpful to geologists? Well, once we have this kind of data, we can then plug it into a computer. So we can use relatively simple computer models which take into account things like the velocity of the seismic wave, the thickness of the crust, and the paths which the ray has taken, and we can use this information to essentially allow us to work out where the crust mantle boundary, which is referred to as the MOHO, is situated. So by using this information and running it through powerful computer programs, we can use it to model the most likely scenario to explain the paths which we're seeing. So how do we use seismic waves to investigate the Earth's deep interior? So you can see here we have a diagram where it's essentially showing the Earth cut straight through the center. Now we know that the Earth obviously has several different layers to it. There's obviously the crust, the mantle, the outer core and the inner core. But how do we actually know this? It's not like we can actually slice the Earth open and look at these layers. So how do we know where they are? And also, how do we know what their physical properties are? Well, the only way for us to get this information is using seismic waves. So in this particular model, we are using an earthquake which has occurred directly under the geographic North Pole in the mantle. So this is our earthquake hypercenter here. So this area here represents the Earth's mantle, and this area here, of course, represents the Earth's core. Now, when we look at the paths which are taken by the seismic waves passing through the Earth, we see that there's a couple of interesting things. So when we look at S waves, we see that we have S waves occurring from here, which is where directly above our earthquake, so our epicenter, and round to 103 degrees from the epicenter. And we can detect S waves all the way from here to here and from here to here. However, when we go from 103 degrees all the way around to 103 degrees over here, we get no S waves being received by seismic stations. So this area where we get no S waves occurring is referred to as the S wave shadow. So we need to explain why the S wave shadow occurs. Now, when we look at P waves, what do we see? Well, just like the S waves, we can detect P waves from here, which is 0, all the way around to 103 degrees, here and here. Now, we then enter a region where we get no P waves produced by this particular earthquake being detectable. So we don't detect them here, and we don't detect them here. So between 103 degrees and 142 degrees, we receive no P waves, and that's the same either side. Now, this is referred to as the P wave shadow. Now, between 142 degrees here and 142 degrees here, we can see that we begin to receive P waves again at our seismic stations, which are produced by this earthquake up here. So we need to explain why we see these P and S wave shadows in the seismic data which we collect. So let's begin by looking at these seismic wave paths which we can see up here. So in these seismic waves, we can see that the seismic wave is essentially being produced by an earthquake which is taking place in the Earth's mantle, and the seismic waves are moving through the Earth's mantle, so they're never moving between layers. This means the material they're moving through is relatively homogeneous. So because we know it's relatively homogeneous, we know what the physical properties of the material should be. So we know, number one, how quickly the wave should be moving, and number two, what kind of paths they should be taking. So we know if the earthquake's here, we know, right, how long should it take the wave to travel from here to here, and how long should it take the wave to travel from here to here. And the kind of data we get matches perfectly with our models. So we therefore know that our wave is traveling through the mantle, and the mantle is relatively homogeneous, because if it wasn't homogeneous, if it was heterogeneous, we would see the waves refracting. So they would arrive in the wrong place at the wrong time, because they'd be moving between, fast and slow materials. However, we don't see that, and so that means that our mantle must be relatively homogeneous. Now, when we move past 103 degrees, what's happening to our S waves? So S and P waves are taking these paths and they're being detected where and when we expect them to. Now, under normal circumstances, we would initially at least have expected S waves to also be detectable from here to here, but they're not. We have our S wave shadow. So the question is, well, what's causing that? And the S-wave shadow is the result of the core. More accurately, it's the result of the fact that the outer core is liquid. So we know that S-waves cannot travel through liquids. So what's happening? Well, in this instance, if we follow this seismic path here, we can see that this seismic wave is emanating from the hypercenter here. It's moving along. It just moves past the core mantle boundary, and so it makes it here to 103 degrees from the earthquake's epicenter, and the same on the other side. What about this seismic wave right here? So let's pretend this is an S wave. It comes down, it moves through the mantle, and the second it hits the core mantle boundary, it's trying to transition from a solid to a liquid, and the S wave dissipates. It's gone. It dies out essentially. So this means that every single S wave that strikes, or at least tries to pass into the Earth's core, disappears. It's lost. They don't exist anymore. And so this helps to explain the S-wave shadow. So the S-wave shadow gives us two pieces of very useful information. The first piece of information it gives us is that the Earth's outer core is clearly liquid, because that helps to explain why the S-waves disappear. The other piece of information that we get is by detecting where S-waves can be identified by seismic stations, we can use it to work out the diameter of the core as well. So we can see here that this seismic wave manages to pass unhindered to the monitoring station right here, and this seismic S wave manages to pass unhindered to this monitoring station right here. And so this means that we can essentially draw a circle within our Earth, and we can use that to work out what the diameter of our core is. So we've gotten two pieces of information straight away. We now know the outer core is liquid, and we know the diameter of the core. So are there any other bits of information that we can get? Well, now let's think about our P-wave shadow. So the P-wave shadow occurs between 103 degrees and 142 degrees on both sides of the Earth. So we need to explain why we're not receiving any P-waves in these areas. Now, we know that P-waves can travel through both solids and liquids. So we know that P-waves will be able to move through the solid mantle and the liquid outer core. We also know that as the seismic waves transition from a faster to slower material, the wave will refract. And so we can use this information to help us work out some more information about the outer core. So, okay, so let's look at our seismic ray paths here. So here's our hypercenter once again, where our seismic waves are being generated. And as we've discussed earlier, our P and S waves are going to take these paths here unhindered. Now, when the P waves are moving down and they try to transition between the mantle and into the outer core, they are essentially moving from a faster material into a slower material. So this is going to cause the angle of the seismic wave to steepen. It's going to refract. And so we can see that right here. If we track this P wave here, it's moving through the mantle. Everything's going quite well. It's quite happy. Then it hits the core mantle boundary right here. And all of a sudden we see the angle it's taking steepen up. Now imagine that the core wasn't here. Well, instead we would expect to see our wave just continue on the same path and it would appear somewhere around there. Now, however, our wave has actually been refracted. So as it's crossed the boundary, it's steepened up. So we can see that with this path right here. So here it goes, it's steepening up, it's taking a slightly curved trajectory, so it's moving through the outer core, and then here it's transitioning back across the outer core mantle boundary. So now it's moving from slow to fast, and so in this case we're going to see the wave's angle become shallower. And so we can see that here. And so we can use the transitions between the mantle and the core to help explain why we have the P wave shadow here and here. It's all down to the refraction. So we know that we're moving from a faster material, which is the mantle, to a slower material, which is the outer core. So what information can we get from this? Well, we already know that the outer core is liquid, and we already know the diameter of the outer core courtesy of the S wave shadow. But what about this P wave shadow? Well, this can also tell us something about the physical properties of the outer core. So for instance, how quickly the P wave can move through the outer core tells us something about how much of the outer core is liquid and what portion of it is solid. It also tells us more about the physical properties of the outer core. So for instance, we can look at some different models about what the outer core might be made of, and so we can then apply those parameters to the data we're getting. We can say, right, if the outer core was made out of this, how would we expect the paths taken by the seismic waves to change? If it's made of this material, how would we expect the seismic waves to change their path as they transition from one material to another? So we can use this information to help us gauge what the outer core is made from. Now, when we're looking at the waves which are traveling through the core itself and taking a more direct route, so from north to south in this model, what can we see? Well, we can see that our waves are coming straight down. They're transitioning as they cross the core mantle boundary. They are going to refract ever so slightly because they're moving from a faster material to a slower material. They then move through the Earth's core. They come out on the other side. They're going to refract ever so slightly because now they're moving from slow to fast, and then we're going to detect them at our monitoring stations around here. So that's pretty much as you would expect. However, when they were looking at this data, they realized something which was a little unexpected. So what they realized was that, bearing in mind we knew what the mantle is made from, and so we know its physical properties, and we know approximately what the liquid outer core is made from, so we know how the wave should be moving through that, so we know where they should be going and at what speed they should be going. Now, what we've realized is that the waves which were arriving down here are arriving slightly earlier than we would expect. So the question is why is this happening? Well, the obvious answer is that there is a solid inner core right here. So what this means is, as our waves are passing through, they're moving through the mantle, which is solid, so they're moving quite quickly. Then they move into the liquid outer core, so they begin to slow down. Now, if it was just a completely liquid core, we would be able to model how long it should take the wave to move from one side to the other before re-entering the mantle, and so we know how quickly how much time the wave should take to arrive at this location here, for instance. Now, what we find is that this wave is arriving earlier. So this would suggest that our wave is moving through the liquid outer core and then it is entering a solid inner core. Obviously, because it's now moving through a faster material, the wave begins to pick up velocity again. It begins to move faster. It accelerates because it's moving through a solid. And so as our wave moves through our solid inner core, it begins to speed up. It then re-enters the liquid outer core and then moves into the mantle. Now, because it picked up that little bit of extra speed as it moved through the Earth's inner core, Well, that means the waves are going to arrive ever so slightly early at the seismic receiving stations down here. And so we can use this information to work out that we have a solid inner core, and we can also use it to work out the diameter of our inner core. So think of these seismic paths here. So this one, this one, this one. They never enter our solid inner core. So we know how quickly they should be moving through the liquid outer mantle, and so we know when they should arrive at the monitoring stations right here. In contrast, these ones that are moving through the inner core are going to arrive slightly earlier than we would expect. So all we have to do is we just have to simply look for the seismic waves that are arriving slightly earlier, so we know they've gone through the Earth's solid inner core, and then we simply have to say, right, well, where do we see these seismic waves appearing that are arriving slightly too early? And we're going to use a similar idea to the one we use for the S wave shadow. We're going to use the seismic waves that speed up to tell us, right, what's the diameter of our Earth's inner core? And so this is how we know that there's an inner core and an outer core, and we know that the outer core is liquid and the inner core is solid. So we can use these P and S waves to help us model the Earth's interior, and so this is how we know, the thickness of the layers and also the physical properties of the layers. Are they liquids? Are they solids? All right, thank you for watching, everybody, and have a good day.